Hello and welcome to Selection with Sathi. Today we are going to cover one of the most important topics in all of computer science. What is DSA? DSA stands for Data Structures and Algorithms, and it is the foundation of everything you will learn in programming. Whether you are preparing for GATE CSE, placements, or coding interviews, this topic is where it all begins. In this video, we will understand what data structures are, what algorithms are, what abstract data types mean, the different types of data structures, and most importantly, why DSA matters for your career. Let's get started. So, what exactly is a data structure? In simple terms, a data structure is a way to store and organize data so that it can be accessed and modified efficiently. Think of it like a bookshelf. You could throw all your books in a pile on the floor, and you would still be able to find any book eventually. But if you organize them on a shelf, alphabetically or by subject, finding a book becomes much faster. That's exactly what data structures do for your data. Data structures are broadly divided into two types. Linear structures like arrays, linked lists, stacks, and queues where data is arranged in a sequence. And nonlinear structures like trees, graphs, and hash tables where data has more complex relationships. The choice of data structure depends on what operations you need, how frequently you perform them, and the type of data you are working with. Now let's talk about algorithms. An algorithm is a step-by-step set of unambiguous instructions to solve a given problem. The key word here is unambiguous. Every step must be clear and precise. A valid algorithm must have 5 properties. First, it takes some input. Second, it produces at least one output. Third, finiteness. It must terminate after a finite number of steps. Fourth, definiteness. Each step must be precisely defined. And fifth, effectiveness. Each step must be basic enough to be carried out. Every algorithm follows the pattern, input goes to process goes to output. The two main criteria to evaluate an algorithm are correctness, meaning it produces the right answer, and efficiency, meaning it uses minimal time and space. Remember, for the same problem, there can be many algorithms, but they can differ dramatically in efficiency. Now here's a concept that GATE loves to ask about. Abstract data types, or ADTs. An ADT is a mathematical model that defines a data type by its behavior from the point of view of the user. It specifies what operations can be performed, but not how they are implemented. Think of it like a TV remote. You press the volume button and the volume changes. You don't need to know the electronics inside the remote. That's abstraction. For example, a stack ADT supports push, pop, peek, and SMT operations. You can implement a stack using an array or a linked list, but the user interacts with the same interface either way. A queue ADT supports enqueue and dequeue. A list ADT supports insert, delete, and search. The key idea is that the implementation can change without affecting the code that uses the ADT. This is the foundation of good software design. Let's now classify all data structures systematically. At the top level, we have primitive and non-primitive. Primitive data structures are the basic types built into the language: integers, floats, characters, and booleans. Non-primitive data structures are built using primitives. Non-primitive structures are further divided into linear and nonlinear. Linear means elements are arranged in a sequence. Arrays, linked lists, stacks, and queues are all linear. Nonlinear means elements have hierarchical or networked relationships. Trees and graphs are nonlinear. There's another important classification: static versus dynamic. Arrays are static because their size is fixed at creation time. Linked lists are dynamic because they can grow and shrink at runtime. When should you use which? If you need fast random access by index, use an array. If you need frequent insertions and deletions, a linked list is better. So why should you invest time studying DSA? Let me give you 4 compelling reasons. First, DSA lets you write efficient code. The same problem solved with the right data structure can be 10 times or even 100 times faster. A linear search takes 1000 steps for 1000 items, but a binary search on a sorted array takes just 10 steps. Second, DSA is required for GATE CSE where it carries about 30% of the marks. And in coding interviews, every single round tests your DSA knowledge. Third, DSA is the foundation for every other subject in computer science. Operating systems use trees and queues for scheduling. Databases use B-trees for indexing. Compilers use stacks for expression evaluation. Networks use graphs for routing. Fourth, every real-world system you use is built on DSA. Google search uses graph algorithms. GPS navigation uses Dijkstra's shortest path algorithm. Social media friend suggestions use graph traversal. DSA is not just theory, it powers the technology around you.
Let's see a practical example to understand why DSA matters. Imagine you have a phone book with 1000 contacts and you need to find a particular name. The naive approach is linear search. You start from the first contact and check each one by one. In the worst case, you check all 1000 entries. That's O of n, so 1000 comparisons. Now if the phone book is sorted alphabetically, you can use binary search. Open the middle, decide if the name is in the first half or second half, and repeat. Each step eliminates half the remaining entries. For 1000 contacts, binary search needs at most 10 comparisons. That is O of log n, same problem, same data, but 100 times fewer steps. This is the power of choosing the right algorithm. Let's look at another example with student records. Suppose you need to store records of 100 students and frequently look them up by roll number. If you use an array, you can store student at index equal to roll number. Looking up any student is O of 1. Instant. But what if students join and leave frequently? Inserting a new student in the middle of an array means shifting all subsequent elements. O of n. A linked list solves this problem. Inserting or deleting a student takes O of 1 if you have a reference to the right position. But now searching for a student by roll number takes O of n because you have to traverse the list. So which is better? Neither is universally better. If your application does more searches, choose an array. If it does more insertions and deletions, choose a linked list. This trade-off analysis is what DSA teaches you. Now let's trace through a stack ADT to see how it works. A stack follows LIFO, Last in, first out. Think of a stack of plates. The last plate you put on top is the first one you take off. Let's trace the operations. Push 10. The stack now contains just 10 at the bottom. Push 20. Now the stack is 10, 20. With 20 on top. Push 30. Stack becomes 10, 20, 30. With 30 on top. Now we call pop. Since it's LIFO, 30 gets removed from the top. Stack is back to 10, 20. Now we call peak. Peak returns the top element, which is 20, but it does not remove it. The stack stays 10, 20. All three operations, push, pop, and peak, run an O of one time. That's the beauty of the stack ADT. Let's connect DSA to the real world, because many students think DSA is just academic theory. Think about Google Maps. When you ask for the shortest route from point A to point B, the app uses Dijkstra's algorithm running on a graph data structure where cities are nodes and roads are edges with weights. Think about databases. When you search a table with millions of rows, the database uses B trees and B plus trees for indexing. Without these tree structures, every query would scan the entire table. Think about your code editor or compiler. When it checks if your parentheses are balanced, it uses a stack data structure internally. And when social media suggests friends you might know, it runs graph traversal algorithms like BFS and DFS on the social network graph. Every large system you use daily is built on DSA.
Before we wrap up, let me share 4 important tips. Tip 1. DSA is not about memorizing. Understand why each data structure exists and what problem it solves. When you understand the why, you will naturally remember the what and how. Tip 2. Start with arrays and linked lists. Everything else, stacks, queues, trees, graphs, is built on top of these 2 fundamental structures. Tip 3. Gate pattern. Gate tests your understanding, not your coding ability. They will ask you about time complexities, trade-offs, and comparisons. Know your complexities by heart. Tip 4. Practice on paper first, then code. Drawing data structures by hand and tracing through algorithms step by step builds a much deeper intuition than just typing code on a screen. That was our complete introduction to data structures and algorithms. We covered what data structures are, what algorithms are, abstract data types, all the different types of data structures, and why DSA is so important for your exams and career. This is just the beginning. In the next videos, we will dive deep into arrays, linked lists, stacks, queues, trees, and graphs one by one. For more concept videos like this, download the Selection with Sathi app. Like and subscribe. Thank you.